Alright, so in this video we will be talking about a chi-square test for independence. So this is a statistical tool to compute for um, the relationship of two variables, two categorical variables. So in our example here, we have men and women. So it's similar to the idea of gender. I know it's sex. Okay, so men and women, and the other one is the type of animals, which are cats and dogs. So it's like asking, or this study, it's like a study where you want to know if it matters, the sex matters of the preference of the type of animal, either cat or dog. So whether the man wants dogs and women wants cat compared to men. So it's something like that. Okay, so it's very simple study, but the point there of this example is just to how to compute manually the chi-square test for independence. Again, it's a non-parametric test, so it is no problem with the number of the assumptions for parametric test, like the test of normality, the Leibniz test. So you don't need to do that. The important thing here in chi-square is you have to have a lot of participants. Okay, so anyway, usually the survey of studies that is using chi-square test is just very simple, just like this, where the participants just need to check whether they are men or women, and then check which one they prefer, cat or dog. So it's simpler when you have a study that requires a chi-square test for independence. But as I said, that you need to have a lot of participants in this kind of study. All right, so here in our data, so we have 207 men who prefer cat, and 282 prefer dog. So we're gonna put the total for men and for women. So there are all in all 489. So this is the total. And for women, 200 there are 231 of them prefer cat, while 242 prefer dog. And all in all, there are 473 women, all in all. So a total of 962, if we're going to add this, 962 participants, all in all, both men and women. So if we're gonna add the total number of men and women who prefer cats are 438, while the total men and women who prefer dogs is 524. So still, it's gonna be the same overall total. It's 962. So this is also total. Next is, we are going to know or compute the chi-square for each of these cells. So we're gonna call it cell. So there are four cells here. And what is the formula for chi-square test? So chi-square, it's called chi-square because of its symbol. It is using the Greek letter chi. So chi is like this. Sorry. So chi is somewhere like that. It looks like an X. That's why usually we use X, literally an X, and then we put square. That means it's a chi-square, but it is called chi because the symbol is not actually X. It's a Greek letter chi. So it's something like that. That it looks like an X. That's why we just make it simpler and look like an X, and we just simply write X. But that's the reason why it's called chi-square. So because it's a chi symbol and then there's a square. So let's just write, make it simple. So just put an x and then square, that's chi-square, equals, and then the formula is observed. Observed is the data, the real data that you have, minus the expected value. So the expected value will still be computed, squared divided by expected value. So we're gonna subtract the observed minus the expected. Okay, so first is, how do you compute the observed value? So each cell here, there are 4 cells important here. Each of these 4 will have an expected value. The expected value is the ideal distribution, meaning it's equal, totally equal proportion for each of these cells. So the not necessarily the same values, but because it depends on how many, or it depends on the weight for each of each cell. So the point there is the expected value is equally distributed according to its proportion for each cell. The observed is the real data. Okay, so let us compute for the observed. So I mean the expected value. So we're gonna copy. We will copy we're gonna create another table. So we'll just write it here at the side, and we'll just use some abbreviations to make it simpler, because what we are after is the expected value of each of these 4 cells. So for this cell, okay, so we have 4 cells, as I said. For men who prefer cats, the expected number of them. So you might want later on we'll be having some decimal values, and do not mind if there are decimals, even if we are talking about men or people, because anyway it's just an expected value. So do not worry about decimals. Do not round it up or round it off to make it whole number. Just leave it as decimals. So how to compute the expected value? You're gonna multiply this total, both total. Okay, so since it is targeting this and this, okay, so I'll just change the color for this. So we're gonna use 438 and 489 because we're solving this cell. Okay, so 438, so it's 438 times 489 divided by the total, this one, 962. So divided by 962. So you are going to compute that using a calculator. So by using calculator, you will get this value. So let me just write right away the value. It will be 222.64. So that is the expected value, meaning the expected number of men who should prefer cat according to your data. So that we can say that there is no significant relationship between these men and women and cat or dog. Now, if your observed data is different from your expected value, that means there is relationship. Okay, so that is what we are trying to know, whether your observed data is different from your expected value. So if the observed data is different from expected, then that means there is a relationship between the two, because that means there is imbalance. Okay, meaning it might be many women prefer cat and many men prefer dogs. So there is imbalances. That means there is something, there is relationship. You can conclude something out of that. All right, so let's continue. For men who prefer dogs, so we're gonna compute, multiply. All right, sorry. So we will multiply 489 and this, okay, because we are talking about this for these cell dogs. So 489 times 500 times 524 divided by the grand total 962. So that's how you do that. How to do it to compute for the expected value, because we need the expected value for the for our computation as based on our formula. It's here. It's E. The observed is already given. That's the data. Alright, so let's continue. If you're going to multiply divided by 962, you will get 266.36. Okay. So we're gonna do the same procedure for women. So I'll just write right away the value, 215.36. And for the dogs and those women who prefer dogs, 257.64. Alright, so that is the expected value. Now we're gonna create another column. Table. So another table. Men, women, for cats, dogs. Now this time, we will be putting in our 4 cells, we will be putting the chi-square for each of this cell. Okay, so we will be computing by the way, in our formula, it must be the sum. Okay, sum or the total. I think I forgot to put summation, but it's so anyway, it's the total. Okay, so because there are 4 cells, so there are 4. It's gonna be 4 chi-square values, and we're gonna get the total for each of this. Okay, so we're gonna compute using the formula observed minus expected, and then square it divided by expected. So it's like this. For this cell for cats, it's 207. That's the observed. Minus expected is this 222.64. 222.64. So again, do not round off unless it's more than 2 decimals. Round off to 2 decimals, and then square the answer. So it's expected that there's no negative answer for this because it's squared, divided by expected. So we'll just copy the expected, 222.64. So you will do the same for the rest of the cells. Observed minus expected squared all over 222.64. So yeah, but that's just for that cell. So again, square of observed minus expected divided by expected. So let's remove it and let's have the answer now. The answer for this is how much it is? 1.099. Okay, so or you can have it in 2 decimals. No, it's 3 decimals because it's the final answer. It's chi-square, so usually it's up to 3 decimal places to make it more accurate. Then we will do the same for the those men who prefer dogs. It's the same, 282. 282. That's observed minus the expected is 266. This one. 0.36 squared divided by expected, so we'll just copy it. 266 minus 36. So it's gonna be like that, and it's going to be the same procedure for the rest. Okay, so the answer for that is 0.918 if you're gonna compute that using your calculator. And then we will do the same for the rest, so I'll just fill in the answers, 1.136 and 0.949. So the same procedure. observed square of observed minus expected divided by expected value. So you have to be careful in computing this, because if you have mistakes in the first table, it will be having a domino effect. The same with the if you create mistake with the expected value table, it will have an effect to the next table. So they are connected to each other, so that you have to be careful for each table. Now after that, we're gonna add it all. 1.099 plus 0.918 plus 1 plus 1.136 plus 0.949. So it will sum up to 4.102. So that is your chi-square value, and we're not yet sure if it's significant or not. So we need the critical value for the chi-square, or the chi-square critical. Chi-square critical, we are not yet sure, or so we'll name it chi-square crit. So how will you know the critical value? So we're gonna use the chi-square table for a while. I think I haven't prepared it yet. Chi-square table. Wait. Chi-square table paint. Where is it? Paint. It's here. Alright. So this is the chi-square table, and it is standard. Okay, so it must be the same for all tables, as long as your source is legit. Now we are going to identify the degrees of freedom. So by the way, we need to compute the degrees of freedom. Sorry. So the degrees of freedom for a chi-square table is so let's compute. As I said before, degrees of freedom is having a different formula for each statistical tool. So it's not the same formula for every statistical tool. Different formulas. Okay, so degrees of freedom for chi-square is the row minus 1, number of rows minus 1, times number of columns minus 1. So in our table, in the original table, anyway, it's the same column and rows for each for the three tables. There are 2 rows and 2 columns, so it's 2 minus 1 times 2 minus 1. So that is 1 minus 1 times 1, which is 1. So the degrees of freedom is 1. Now going back to our table is okay, so it's here. So the degrees of freedom will be 1, and our alpha depends on the given. So let's just assume that this is an alpha of 0.05, meaning 5% chance of error. Okay, so this is a level of significance in our given, and usually it's 0.05. So 0.05, so it's here. No more one tail and two tail, so it's automatic two tail for chi-square. There's no such thing as one tail for a chi-square distribution. So our chi-square critical value is 3.841. So let's remove now our table. It's 3.841. Now for us to say that there is significant relationship, okay, there is relationship between the two categorical variable, the sex and the type of animals, cat and dog. The chi-square value must be bigger than the chi-square critical. Okay, so since the chi-square 4.102 is greater than the chi-square crit, which is 3.841, Oh wait, where did I put comma here? Therefore, we reject HO, or the null hypothesis. So the null hypothesis is saying that there is no significant relationship between the sex and the type of animal to choose. So that means it won't matter whether you're a man or man or woman, whether you choose cat or dog. So it won't matter. But that is not the case in our computation. It says that we reject the null hypothesis. That means it matters whether if you're a man, you prefer more dogs than cat. If you are a woman, then that means you prefer cats. So yeah, you just have to balance with your conclusion on the data. Okay, so for men, they prefer dogs. For women, they prefer it won't matter for women. For men, it matters. Okay, so yeah, guess for women, 231 for cats and 242 for dogs. But the point there is, it is saying that there is significant relationship, that it matters, that the gender or the sex matters on the preference of the type of animals. Alright, so that's all for this video.